All right, so let's get started. So we are discussing two ways in which, given two linear vector spaces, we can construct higher dimensional linear vector spaces. So let's quickly recap what we did yesterday, and that will set the stage for what we're going to do today. And yesterday we discussed a way of constructing a higher dimensional vector space called the direct sum. So recap. Right? So given two vector spaces V and W, we constructed a higher dimensional space, which we call the direct sum of V plus W. Okay, it's denoted by a plus with a circle around it. And if this vector space is an n-dimensional vector space and this vector space is an m-dimensional vector space, then this V plus W, the direct sum of these two vector spaces, is an n plus m dimensional vector space. Okay. Excuse me. So if the vectors in V can be represented as n entry column vectors, and if the vectors in W can be expressed as m entry column vectors, the vectors in V plus W, are plus n entry column vectors. Okay. And then we want to understand how to write down operators on this particular direct sum space, but we wanted to write down operators with a particular constraint. So we asked the question, if A is an n by n matrix, that is a mapping between the space V to itself, and if B is an m by m matrix, that is a mapping from W to itself, then what is the matrix that one should write down in this n plus m dimensional vector space that preserves both these mappings? Okay, so it is clear that the matrix in n plus m dimensional vector space, if it has to act on these vectors, it has to be n plus m cross n plus m matrix, right? So the matrix in V plus W that acts on the direct sum vectors V plus W is an n plus m cross n plus m square matrix. Okay. So we asked the question, what should the form of this matrix be? So let us call this matrix the direct sum of the two matrices A plus B. We don't yet know what is A plus B, but we asked the question, what should be the form of this matrix A plus B such that A plus B acting on the direct sum of the two vectors V plus W is equivalent to simply the direct sum of the vectors AV and BW. So I want this to be equal to AV plus BW. In other words, the mapping is preserved. Even in this direct sum space, the matrix A only acts on the V components of the direct sum, and the matrix B only acts on the W components of the direct sum. Okay, and we found out that such the matrix that satisfies this property is necessarily of a block diagonal form. Okay, this was the gist of what we learned yesterday. So today we will learn a new way of constructing a higher dimensional vector space, and this is called a direct product or a tensor product space. Direct product, or sometimes called tensor product space. Okay. So we will again proceed with the construction of this space methodically, just like we did with the direct sum. We will first figure out what are the two vector spaces that we are dealing with, and we proceed to multiply them in this case. Okay, so we'll explain what it means by multiplication, and then we will construct a new space that is a higher dimensional space. So the point is here is that if V, so we will start with two vector spaces, start just like we did for the direct sum, start with V, an n-dimensional linear vector space, and W, which is an m-dimensional linear vector space. Okay, so V, on V, the set of basis vectors that span the V space, we denote as we did yesterday by E1, E2 till En. Okay, with the condition that Ei dot Ej has to be equal to delta Ij, just like basis vectors ought to be. Sorry, excuse me. On the space W, we will define a set of basis vectors F1, F2 up to Fm, okay? And Fi dot Fj should be equal to delta Ij, okay? Because these are all proper basis vectors and we want them to be orthonormal, okay? So now we define a direct product space. Now we define a new direct product space, which is a higher dimensional space, and define a new higher dimensional space with nm basis vectors, n times m basis vectors. Okay, unlike in the direct sum case where the higher dimensional space was n plus m dimensional, in the direct product case, the higher dimensional space is nm. So I will denote the basis vectors in this space with the notation Ei cross Fj, with a cross encircled by a with a circle around it. Okay, we'll understand what this symbol means and how to calculate this quantity. But this is what we are doing. We are constructing a new higher dimensional space that is of dimension nm. So if n is 2 and m is 3, the direct sum space would be 5-dimensional and the direct product space would be 6-dimensional. Okay. All right, so now we have to figure out what these basis vectors are and how to construct them, and again how to define vectors in this space, how to define matrices in this space, and then we will ask the exact same question we asked for the direct sum case. So what should be the form of the matrix in this higher dimensional space? This time we will call it A times B or A cross B, such that A cross B acting on the vector in this higher dimensional space would give me A times V cross B times W. Okay, so I'll make this more precise as we go along. The question that we ask is exactly the same. So we want to construct a new matrix in this higher dimensional space that preserves the mappings. Okay, so what are the vectors? So again, it's easiest to work with an example. So let me take n equals 2 and m equals 3. Okay, so I can write my E1 vectors as 1, 0 and 0, 1. And my F1 would be, I will write everything in excruciating detail. 0, 1, 0 and F3. These are the three basis vectors I have. 0, 0. Okay. So now I want to construct a new 6-dimensional space, which is 2 times 3 is 6-dimensional space. So I need 6 orthonormal basis vectors. So I'll have to construct the basis vectors out of E and F. Now remember what we did for the direct sum case. For the direct sum case, we simply stack the vectors on top of each other, right? So we simply claim that the new space should be 5-dimensional. So for example, we took E1 and then we just simply added zeros. Here we are going to construct it in a slightly different fashion. So E1 direct sum F1. Okay, so what is this? So again, the way you construct this is by multiplying every entry in the first vector with every entry in the second vector, with the matrix of the second vector. So what does this mean? So here I have two vectors, 1, 0 and 1, 0, 0, right? So the way I construct the basis vector in this direct product space is first I take the first element of this guy, okay? And then I multiply every element of the second matrix with the first element of this guy. So 1 times 1. So the first entry here would be 1 times 1, 1 times 0, and 1 times 0. Okay, these will be the first 3 elements of my 6-dimensional basis vector. Okay, now I do the exact same procedure again. I take the second element, okay, and then I multiply it with the first element here, first element, second element here, and third element here, and I construct the other 3 components of this basis vector. Okay, so let me actually do it completely out, and we will do everything here. So what is the first element? It is 1 times 1. Second element is 1 times 0. And the third element is 1 times 0. The fourth element is now 0 times 1. Then 0 times 0. Then 0 times 0. Okay, this will be the first vector E1 cross F1. And as you can see, this is a 6-dimensional vector. Okay, it has 6 different components. Excuse me. Okay, so let us actually do everything out. So let us calculate E1 cross F2. So again, E1 is 1, 0 and F2 is 0, 1, 0. So this vector would be, take the first element, which is 1, right? And then multiply it with all 3 elements of the second guy. So I'll get 0, 1, 0. Then take the second element of the first vector, which is 0, and multiply all 3 elements of the second vector. I'll get 0, 0, 0. This is my second vector. The third one is E1 direct product F3. So this is 1, 0, 0, 0, 1. So again, take the first element of the first vector, which is 1, and multiply every single element of the second guy. So you get 0, 0, 1. Second element is 0, so you get 0, 0, 0. Okay, so now we can see a pattern emerging and you can fill everything in, but I encourage you to just do it out completely. So E2 direct product F1 would be 0, 1, 1, 0, 0. So what is this? This is, take the first element, oops. Take the first element, which is 0, and multiply every single one term by term. So 0, 0, 0. Take the second element 1, multiply everything. 1, 0, 0. E2 cross F2, 0, 1, 0, 1, 0, 0, and then 0, 1, 0. And the last one, which is E2 direct product F3, would be computed as 0, 1, 0, 0, 1. And this would be equal to, again, take the first element, multiply all 3, you get 0, 0, 1. Take the second element, you multiply all 3, you get, 0, 0, 0. Take the second element 1, multiply all 3, you get 0, 0, 1. Okay, so these are the 6 vectors in the 6-dimensional linear vector space, that is V, excuse me, V cross W. Okay, V cross W is thus spanned by the 6 vectors EI, Fj. Okay, the reason it is called tensor space is basically because the basis vectors here have 2 indices as opposed to just 1 index, right? EI, Fj. It is not just EI, so E1, F1, E2, F2, and E3, F3, and there is just not just 1 index. There is actually 2 different indices. So you take the E along the first direction in the first basis and take the direct product with F along any one of the 3 directions in the second basis. Okay, so there is necessarily 2 indices. So that is why sometimes it is called a tensor space. Okay. Any questions about the construction of these basis vectors? So it is slightly more involved than the direct sum space, but it is straightforward enough for you to understand. So how does a direct product vector look like? So V cross W. Well, let's write this out. V in the n-dimensional space, for example, is written as I equals 1 to n Vi Ei, right? Direct product, for example, J equals 1 to m Wi Fj, sorry, Wj Fj, right? So Vi and Wj are numbers, which are components, and Ei and Fj are vectors. So I can write this as I equals 1 to m, J equals 1 to m, Vi Wj times the direct product of the basis vectors. Okay, so since we have computed the direct product of the basis vectors, for at least a simple example, you can simply use this to calculate what the direct product of two vectors would look like. So for example, in our case, n equals 2 and m equals 3, V cross W would be, the way you do the sum is first fix I and sum over all three j's, and then choose the second value of I and sum over all three j's. So in this case, this is I equals 1 to 2, j equals 1 to 3, Vi Wj Ei cross Fj, right? So the way you do this double sum, which might be easy to you, but I'll just work it out in any case. First, let me fix I equals 1, so V1, and then I will sum over all three values of j. So I'll have W1 times E1 cross F1 plus W2 E1 cross F2 plus W3 E1 times F3. And then I will fix I equals 2. This is V2 times. Then again, I'll sum j from 1 to 3. So W1 E2 times F1 plus W2 E2 F2 plus W3 E2 direct product F3. Okay. If you want to write it in a column vector notation, you can easily figure out that this can be written by simply substituting your column vectors for E1 cross F1, E2 cross F2, and things like that. You can write this column vector as V1 W1, V1 W2, V1 W3, V2 W1, V2 W2, and V2 W3. Okay, so this is how the direct product of two vectors looks like in the six-dimensional basis, six-dimensional linear vector space. Are there any questions? Before we move on to matrices, are there any questions about how to construct these vectors?
Hello, sir.
Yeah.
Sir, when you are saying that Ei cross Fj, okay, it has two indices. One is I, another is j. So instead of matrix Y, it's a column vector.
Instead of matrix Y, it's what?
Why it's a column vector? I mean, it should be matrix now because it has two indices, so it can be n cross n something matrix.
No, it is not a question of what it can be. Okay, the question is, I want to write down a set of basis vectors. So I want to write down a rule of multiplying two vectors to give me a third vector. So this is a new way of multiplying two things. So there is two objects in a linear vector space. There are vectors and there are operators, right? Or matrices for mathematicians, operators in quantum mechanics. So vectors are basically columns, and then matrices are n by n blocks or whatever blocks that act on these vectors. So whenever I define a higher dimensional space, I have to define both these objects. I have to define column vectors and I have to define objects that act on these column vectors. Those are two different things. I cannot confuse the two.
Okay, sir.
Of course, I can take two column vectors and do an outer product and write a matrix, but that wouldn't serve my purpose because that wouldn't function as basis vectors, right? There is no way in which I can define orthonormality of things.
Yes, sir.
Sir,
Yes.
how can I visualize this direct product? I mean, what are we exactly doing? Mathematically, I understand, but if I had to picture it.
So the best way to picture it would be to wait for one more lecture where I talk about angular momentum addition. So it will actually be
Okay.
simple. So see, the whole point is this, right? See, we say that J equals L plus. In fact, I wrote this down. Oh my gosh, so sorry. I'll stop share and reshare again. Sorry, give me just a second. Okay. So I wrote this down. This looks like a very innocuous equation to write down, right? But the point is, whenever you, so when you go to the nitty gritty of it, when you write down when you work out the quantum mechanics of the situation, you realize that on the Hilbert space, uh, a physical rotation is realized as matrices, right? That act on the vectors in the Hilbert space. Now, nobody told you what the dimension of these vectors are, right? We never fixed the physical system. We said we started with a physical rotation. We simply said that this is realized as some kind of a rotation in the Hilbert space, but we never said that we are living in a one-dimensional Hilbert space or five-dimensional Hilbert space or infinite dimensional Hilbert space. We just said some Hilbert space. So it should be applicable to a wide variety of Hilbert spaces. So now the next question is, what is the form of these matrices that act on these vectors in the Hilbert space? And then we figured out what the form is, right? So we figured out that the entire rotation matrix in the Hilbert space can be written in a block diagonal form with a 1 by 1 block that acts on only one vector, a 2 by 2 block, which is the j equal to 1/2, that acts on two basis vectors, 1/2, 1/2, and 1/2 minus 1/2, and a 3 by 3 block that acts on three basis vectors, 1, 1, 1, 0, and 1 minus 1, and so on and so forth. So such a kind of pattern emerged, and all this was simply because of the commutation relations between the two different J matrices, nothing else. So the point is, now we are doing something extra. Now I'm saying that I want to add two such generators. But the point is that this is easier said than done, because the ordinary rules of matrix addition don't apply. For example, I can add S equals 1/2 and L equals 1, right? The question is, what is this J matrix? Because there is no sense in which I can say, so suppose if I want to compute the J3 component of L plus S, where L corresponds to 1 and S corresponds to 1/2, then I should take the L matrix, L3 matrix corresponding to L equals 1, which is some H bar times some 3 by 3 matrix, right? And then I should take the S3 corresponding to the S equals 1/2, which is H bar times some 2 by 2 matrix. Agreed? So specifically, this would be H bar times 1, 0, 0, 0, 0, 0, 0, 0 minus 1, plus H bar times 1, 0, 0 minus 1, H bar over 2. Now, how am I going to add these two matrices? This doesn't make any mathematical sense, right? So whenever I say that J is L plus S, I probably mean something different. I need to have a consistent mathematical way of adding these matrices that live in different Hilbert spaces. And the way I will actually interpret this at the end of this lecture would be to say that this is not just L plus S, but this is mathematically slightly more involved, and I should define it with respect to direct products. So once I say that, the connection to whatever I'm saying would be immediate. But before I do that, I want to finish off this mathematics preliminary. That is all. So the physics of this will be apparent once we talk about angular momentum addition, either by the end of today's lecture or next lecture. Is that okay?
Okay, sir.
Any other questions or comments at this stage? Okay. So now let's move on to matrices. Okay. So again, I will ask the same question. Now my space is 6-dimensional, right? So I'll again stick with n equals 2 and m equals 3 because, excuse me, doing it with respect to a single example is easier in some sense. Okay, so now let us say that I define matrices A and B in these two linear vector spaces. So I'll define a mapping in the two-dimensional linear vector space that takes any vector in the two-dimensional linear vector space and maps it onto another vector in the same two-dimensional vector space. Okay, so that is the sense in which I can claim that the matrix A is a mapping from V to V. Okay, from V to V simply means that it takes a vector in V and maps it onto a different vector in V. It doesn't push it out of the linear vector space. Those are the kinds of mappings you're actually interested in quantum mechanics. So let us take two such mappings. So I take V and then map it onto AV, which I can call V prime if I want for notation's sake. What do I exactly mean by this? I mean that I have a column vector in my two-dimensional space, and I have a 2 by 2 matrix A11, A12 that acts on this to give me a new vector, which is plus A12 V2, A21 V1 plus A22 V2. Okay. Similarly, let me define a mapping that maps W onto W. So W BW, which I will call some other vector in the same three-dimensional vector space W. So again, written everything out, W1, W2, W3 equals some 3 by 3 matrix, which I will call B11, B21, B22, B23, B32, B33, acting on W1, W2, W3. Okay, so this will be a new matrix. This will be a slightly more complicated one than the last. So you'll have B11, W1. So this will be the first entry, B22 plus B23, B31, B32, B33. Okay. So now, okay, so this much is very straightforward, but what I want to do is now I want to define a matrix in the product space such that I want to define a new matrix such that A times B. So just like I asked the question in the direct sum, so where was it? So what did I ask here? What should be the form of the matrix in this new higher dimensional space, direct sum space, which I'm going to call A plus B, such that this matrix in the higher dimensional space acting on the vector in the higher dimensional space decomposes into the direct sum of the A acting on the original vector V and B acting on the original vector W. So in other words, all I'm saying is that I'm demanding that the form of the matrix be such that it preserves the mapping. The components of A only act on V and not on W, and the components of B only act on W and not on B. So that is why you have A times V and B times W here. Yeah? So this is what I mean by preserving the mapping. So A doesn't go rogue and change B, change W, and so on and so forth. So I'm going to ask the same question here. So I'm going to ask, what should be the form of the direct product of these two matrices in the higher dimensional space such that AB acting on the higher dimensional vector, in this case V times W, can be simply written as AV direct product BW. It can be written as a direct. So basically, this complicated six-dimensional vector, six-dimensional matrix acting on the six-dimensional column vector should be expressible as this vector direct product this vector. Okay, that is what I'm asking. So this is slightly trickier to figure out than the other one. So we'll do it in steps. So we'll first try to understand what should be the matrix that preserves A. The first mapping, then we will figure out the matrix that preserves the B mapping, and then we'll simply marry them together. Okay. All right. So let us first talk about A. So let us first talk about preserving the without talking about B, let us first write down a matrix that preserves, for example, the mapping from V to B. In other words, I'll set B to be an identity matrix. So now, just like I wrote down a vector multiplying two vectors, I have to write down a new matrix multiplying two matrices. So in other words, I need to figure out how to multiply the a 2 by 2 matrix with a 3 by 3 block, and I will do the exact same. I'll do it the exact same way as I multiplied the column vectors. In other words, let me talk about. So let me ask what should be the form of this direct product of A times I. Okay, why I? Because I first only want to talk about the mapping A, so I don't want to complicate things by putting in both A and B together. So I will talk about the mapping from V to V, and then I'll talk about the mapping from W to W, and then I will talk about both the mappings together. So now I want to figure out what should be the form of the matrix A cross I that when acting on V times W should give me AV times W. Okay. So I'm not complicating it by putting in B also, because I'm simply claiming that the B is I. Okay. So anyway, this is the same thing applied to B equals identity matrix. But whatever it is, I need to figure out what this guy is, right? So let me actually do this out. So A is A11, A12, A21, A22. And B is an identity matrix in the three-dimensional linear vector space, remember. So 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, the way I calculate this, so the product of these guys would be a 6-dimensional matrix. The way I do this is exactly how I did with the column vector. So I'll take every element of the first guy and multiply it by with every other element of the second guy. So first I will take A11, and then I will form a 3 by 3 block of this new matrix by multiplying A11 with every single element here. Okay, that will be a 3 by 3 block. Then I will take A12. Then I'll multiply A12 with every single element in this guy, which will be another 3 by 3 block. Okay, then I will take A21. And then I'll multiply it by every single element in the second guy. That will be the third 3 by 3 block. And then I will take A22, and then I'll multiply it by every single guy here. That will be a fourth 3 by 3 block. So this, as you can see, would be a 6 by 6 matrix. Okay. So this is guaranteed to act on a 6-dimensional column vector. So enough talking. So let me actually do this. So A11, A12, A21, A22, acting on 1, 0, 0, 0, 1, 0, 0, 0, 1 would be the first 3 by 3 block is A11 acting on all these guys. So A11, 0, 0, 0, A11, 0, 0, 0, A11. Okay. The second block would be A12 acting on every single guy. So A12, 0, 0. The third one would be because it's a unit matrix, the multiplication is very easy. The fourth one is A2200. Okay. So this is the direct product of A times I. Okay. Now, what would this guy look like when it acts on a column vector, which is a direct product of V and W? So how does this act on V cross W? Well, let's figure it out. V cross W, as we have already figured out, is V1W1, V1W2, V1W3, V2W1, V2W2, V2W3, right? So what is this equal to? So this is equal to, what is the first element? The first element is A11 acting on V1W1 plus 0 plus 0 plus A12 acting on the fourth one, which is 1, 2, 3, 4, V2W1. So the first element of this column vector would be A11 V1W1 plus A12 V2W1. Okay. So if you are a little careful, you can easily massage this into a form that you already can recognize. I can take W1 common and I can write this as A11V1 plus A12V2. Okay. So what would be the second element? The second element would be A11 acting on V1W2 plus A12 acting on V2W2. So I'll take W2 common and write this A11V1 plus A12V2. And now you see a pattern emerging. The third element would be A11V1 plus A12V2. Okay. The fourth would be, now the fourth is interesting. Now the fourth row of this matrix starts with A21. So I will have A21 times V1W1 plus A22 times V2W1. So I will have W1 times A21V1 plus A22V2. Okay. This would be A21V1 plus A22V2. And this would be A21V1 plus A22V2. This would be the column matrix. That would be the direct product of A times I acting on the 6-dimensional column vector. And you actually see that the first 3 components have W1, W2, W3. The second 3 components also have W1, W2, W3. And W's simply come for the right, but the V's mix between each other, right? So the first V is simply A11 V1 plus A12 V2. But this is precisely the mixing between the V's in the 2-dimensional space, right? So V1 becomes V1 prime, which is A11 V1 plus A12 V2. Similarly, V2 becomes V2 prime, which is A21 V1 plus A22 V2. So I can write this as W1 V1 prime, W2 V1 prime, W3 V1 prime. All right, so let me write it here. So it's equals V1 prime W1, V1 prime W2. These are components, so it doesn't matter which way I write them. Oh man, sorry. I didn't mean to erase that. V1 prime W1, V1 prime W2, V1 prime W3, V2 prime W1, V2 prime W2, V2 prime W3. Okay. So what is this column vector? Well, so V cross W has the form V1 W1, V1 W2, V1 W3, V2 W1, V2 W2, V2 W3. So this is basically V prime cross W. In other words, this is AV direct product W, okay, by direct computation. So if I construct a new 6x6 matrix such A cross I, where I is a 3x3 unit matrix and A is a 2x2 matrix that is the mapping from V to V, then such a matrix, such a 6x6 matrix acting on the composite vector V cross W acts only is such that it is a direct product of the vector AV and W. So I leave it to you to figure out, because I don't have a lot of time, but I leave it to you to figure out, for example, that if you do it the other way around, for example, if you set A equal to 1, set A equal to unit matrix, okay, 1, 0, 0, 1. Don't worry about the mapping in A, but let us worry about the mapping in B. So remember that my direct product space is the direct product of the 2-dimensional space with a 3-dimensional space. But in this case, the mapping in the 2-dimensional space, I'm simply taking to be unity. So what happens if I calculate this? I cross B acting on VW. Okay. If you actually do the calculation, now again, this would be a 6x6 matrix acting on a 6-column vector. So if you do this, you should get something like, can anyone tell me what you should get? What do you expect? See, remember that if I set B to be identity matrix, then the matrix direct product A cross I acting on B cross W would be the direct product of AB and W. Similarly, if I set A to be the identity matrix and B is a non-zero mapping, then this would be the same as the direct product of V with BW. Okay, so this is for you to prove this. Okay. So again, how do you calculate the 6 by 6 matrix I cross B? I cross B now would be, I is a 2 by 2 matrix in the 2 by 2 unit matrix, and B is some mapping B11, B12, B13, B21, B22, B33, and B31, B32, B33. Yeah. What is this equal to? Again, take the first element of the first matrix, which is 1, and multiply every single guy in the second matrix to form the first 3 by 3 block. So that will be B11, B12, B13, B22, B23, B31, B32, B33. Okay. What is the second element? That is 0. So this is trivial. 0, 0, 0, 0, 0, 0, 0, 0, 0. What is the 2, 1 element? That is also 0. So 0 acting on every single element will again give me 0. The fourth element is 1. 1 acting on every single element of the second matrix is going to give me B11, B12, B13. B33. Okay, this will be the matrix I cross B. Okay. So how would this matrix act on B cross W? Well, let us figure it out. So this acting on B cross W would be V1W1, V1W2, V1W3, V2W1, V2W2, V2W3, right? This is the V cross W matrix, the vector. So this would be, the first one would be, the first 3 elements all have V1 here. So this will be V1 times B11W1 plus B12W2 plus B13W3. The second element would be V1 B21W1 plus B22W2 plus B23W3. Remember that since the other things are 0, there is no V2 here. There is no term proportional to V2. That is important because the B matrix is not mixing W's and V's non-trivially. The third one would be V1 B31W1 plus B32W2 plus B33W3. Okay. Again, please stop if there is any questions. If not, this is very straightforward calculation. Then the fourth one would be again B11W1 plus B12W2 plus B13W3. I've written out so far, so I'll also write down the last element. So this is B31 plus B32 plus B33. And what is this column vector? This column vector is nothing but V1 W1 prime, V2 W2 prime. Excuse me. See, this is the kinds of mistakes you should not do. V1 W3 prime, V2 W1 prime, V2 W2 prime, and V2 W3 prime, which by our definition of direct product is the direct product of the two matrices V, direct product of the two column vectors V and W prime, which is nothing but V times BW. Okay. So what have we discovered thus far? We have discovered that a direct product I acting on V cross W gives me AV direct product with W. If I don't do anything in the second basis, I know the matrix in the six-dimensional space that will preserve the original mapping. We have also discovered that if I don't do anything in the first basis, I know the matrix in the six-dimensional linear vector space that will preserve the mapping in the second linear vector space. But what if both A and B are non-zero? What should be the matrix in the six-dimensional linear vector space that preserves both these mappings simultaneously? Well, the answer is actually not very hard to guess. It will be the product of both these matrices. So let us actually verify that explicitly. I am claiming that the matrix that preserves both multiplication, so the matrix that A times B, V times W, that should be equal to AV times BW, right? This matrix, what should be the form of this matrix? That is the question, right? So my claim is that this would simply be equal to A cross B would be equal to, first calculate this and then calculate the other and simply multiply these two matrices. So this is simply an ordinary multiplication. Okay, because this is a 6 by 6 matrix, this is a 6 by 6 matrix, I can multiply two 6 by 6 matrices, no problem. Okay, so let us actually show that this is actually true. I'm not going to ask you to take it for granted. So let us actually explicitly take this form and act it on B cross B and see what we get. So A cross B acting on V cross W in this case would be A cross I times I cross B acting on the vector V cross W, right? So let us do it. So again, the order is important. So first, let me take the matrix I cross B and act it on the vector V cross W. But we already know what the answer is. The matrix I cross B acting on the vector V cross W is the exact same thing as the vector V direct product BW. So this is equal to A cross I times the vector V direct product BW, right? But we also know what A cross I acting on B cross BW is, because A cross I acting on B cross a vector in the second basis leaves the second vector alone and simply takes the direct product of AV times the second vector. So this would be AV direct product BW. And this is precisely what we want. So the matrix, the 6 by 6 matrix, or whatever the nm dimensional matrix would be the matrix that specifically preserves both these mappings would be A times B, where A times B, so let me write this down, A times B, the direct product of the two matrices that preserves multiplication, that preserves the two mappings, is given by A cross I times I cross B. Okay, so it's your job to write down A cross I times I cross B explicitly. So A cross I, you've written it down, is this matrix. Where is this matrix? This is my A cross I. Okay, A cross I, and this is my I cross B. So if you take these two matrices and multiply them together, you will get the matrix A cross B that preserves both these mappings in the six-dimensional linear vector space. Okay, so this is about tensor products. So I'm out of time, so I'll make the connection to angular momentum addition starting next class, and then you'll be able to figure out why is it that we need all this mathematics, because this is the only way we can consistently define what we even mean by addition of two angular momenta, which can in principle be two different angular momenta. Okay. All right.